All right, let's dive in. Today we're looking at a really cool idea. How do you train an AI that doesn't just win a single game, but learns how to keep on winning forever in a kind of endless digital arms race? It's a fascinating puzzle.
You've probably heard this famous quote from Lewis Carroll's Through the Looking Glass. The Red Queen is explaining her bizarre world, and it perfectly captures one of the biggest challenges in evolution, and as it turns out, in artificial intelligence. It's this paradox where you have to run as fast as you can, not to get ahead, but just to stay in the same place.
And this very idea, what's known as the Red Queen's race, is at the heart of what we're talking about today. It's this deep connection between how life evolves on Earth and how we might build truly smart, adaptable AI.
I mean, think about it. In biology, this is called the Red Queen hypothesis. A cheetah can't just evolve to be the perfect predator and then stop. Why? Because the gazelles are also evolving to be faster and more agile. It's a constant, never-ending race just to survive.
And that brings us to the million-dollar question for the research we're digging into. How do you create an AI that's a tough, adaptable generalist, ready for anything, instead of, a fragile specialist that's amazing at one thing but falls apart at the first sign of something new? To figure this out, researchers turned to a really unique digital battleground. And the arena they picked is this wonderfully strange game from the 1980s called Core War. Honestly, it's the perfect little sandbox for watching a digital version of evolution play out.
The concept is pretty simple, but it's also kind of brilliant. You write a tiny program, your warrior, and you drop it into a virtual computer's memory right next to your opponent's warrior. Then you just let them go. The machine runs instructions from both, and the last program left standing wins. It's like a little self-contained digital ecosystem.
And these warriors are written in a language called Red Code. As you can see, this is not your friendly neighborhood Python. We're talking super low-level, assembly-style code. It's the raw, direct language of the machine itself. So to give you a feel for it, here are two classic, super simple strategies. You've got the dwarf, which is basically a bomber. It just starts dropping these little digital landmines everywhere, hoping the other program runs into one and crashes. And then you have the imp, a tiny little virus that just copies itself over and over again, trying to completely overwrite its opponent. And if you could actually peek inside the machine's memory during a fight, this is what you'd see, just pure chaos. The different colors are the code from different warriors. And the crazy thing about Core War is that there's no difference between a program and data. Everything is fair game. They can overwrite, change, and corrupt each other in real time. Okay, so you have this totally retro, chaotic battleground. The next step was to bring a very modern tool to the party, a large language model. The goal was to see if it could be used to evolve some truly elite digital gladiators. To do this, they built an algorithm with the perfect name, the Digital Red Queen, or DRQ for short. It's a method designed specifically to create that evolutionary arms race we were talking about earlier, but inside a computer. Here's how it works, and it's pretty slick. You start with just one simple warrior. Then you tell the LLM, hey, generate a new warrior that can beat this one. Simple enough, but here's the kicker. For the next round, the LLM has to evolve a new champion that can beat both of the previous ones. And you just keep doing that. Every single round, the challenge gets harder and harder, forcing the AI to come up with more and more robust strategies. So just to be clear, the LLM isn't actually playing the game. It's more like an evolutionary coach. It looks at the champions so far, sees what's working, and then suggests mutations or even completely new programs to try to create the next, even better champion. It's the engine driving the evolution. So, what happens when you set this whole digital arms race in motion and just let it run? Well, the results were fascinating and honestly, a little unexpected. They saw clear, undeniable signs of digital evolution in action. First, let's look at the baseline. If you train a warrior against just one opponent over and over, you get what's called a brittle specialist. It's a one-trick pony. It gets really good at beating that one opponent, but against a whole field of diverse, human-made warriors, it only wins or ties about 28% of the time. Not great. Okay, but what happens when you make that AI compete against its entire family tree? When you throw it into the Red Queen's race? The performance just skyrockets. The champions that come out of the digital Red Queen process can win or tie against 62% of those same human warriors. That constant pressure to beat an ever-growing list of tough opponents forced it to become a much more adaptable, robust fighter. Which leads to the next obvious question, right? If you run this whole experiment a few times, do you always end up with the same single perfect super warrior? is there only one right answer to how to win?
And the answer, and this is the really cool part, was a clear no. The code on the inside, the genotype of these champions, was all over the place. The AI found tons of different ways to write a winning program. But their behavior, how they actually fought in the arena, their phenotype, all started to look eerily similar. They all converged on the same winning strategy.
You've actually seen this exact thing in biology. It's called convergent evolution. Just think about wings. Bats, birds, and insects all figured out how to fly. They all evolved wings, but their genetic paths, the underlying blueprints, are completely different. It's different solutions to the very same problem. And that's exactly what happened here, inside a computer. And this visualization shows us exactly why. Look at the chart on the left. That's what happens when you only compete against your last opponent. You get stuck in these endless cycles, like a game of rock, paper, scissors. But on the right, when you have to beat your last 10 ancestors, those cycles just vanish. It forces the evolution of truly general strategies that can't be easily tricked.
Okay, so training digital gladiators in a 40-year-old game is awesome, but let's zoom out. Why does any of this actually matter in the real world?
Well, because this whole method is a blueprint. It's a safe way to automate the discovery of winning strategies in any situation where there's an adversary. In cybersecurity, you could evolve new attacks to find holes in your defenses before the bad guys do. In medicine, you could simulate how a virus might evolve to resist a new drug. You could even use it to automatically red team your own AIs to find their flaws before you ever deploy them. And that leaves us with this one final massive idea. The digital Red Queen isn't really about winning a game. It's about automating an arms race. It's about harnessing the power of evolution itself as a tool for discovery. And it makes you wonder, if we can now do that, what incredible new strategies in science, in security, in, well, anything, are just sitting there waiting for us to find them.